Is it visible? Full screen?
Yes, doctor.
Okay. Hello, everyone. This is Dr. Sucheta Saha. I'm a rehabilitation consultant in the Department of Neurorehabilitation, Institute of Neurosciences, Kolkata, India. And I'm going to present a topic which is very close to my heart, rehabilitation robotics, a step ahead in neurorehabilitation. I have been working with rehabilitation robotics since my post-graduation time. And first, let us be familiar with the word rehabilitation. What is that? It is derived from a Latin word, habile, that means to make able again, and re means again. So rehabilitation as a whole means to make able again. By definition, it is a set of interventions designed to reduce disability and optimize functioning in individuals with health conditions in interaction with their environment. Rehabilitation physician leads a team which consists of physiotherapists, occupational therapists, audiologists, speech, language, and swallowing pathologists, orthotists and prosthetists, rehab psychologist, rehab nurse, rehab health assistant, vocational counselor, social worker, etc. So that makes the whole rehab team. Now coming to robotics. It is the application of electronic computerized control system to mechanical devices designed to perform human function. So do our rehabilitation robots look like this one, which we often see in Hollywood movies? Sorry to disappoint you. They look very bulky and boring, like this too. This is the upper limb robotic device, Spring, and this is the lower limb robotic device, Locomat. So let us begin our discussion on rehabilitation robotics. It is a field dedicated to understanding and augmenting rehabilitation through the application of robotic devices. Robotic technology attempts to leverage the principles of neuroplasticity. Plasticity means the potential for change, and neuroplasticity is the reorganization of the surviving CNS element that supports neural recovery after any neurotrauma by means of axonal sprouting, unmasking of the previously inactive sinuses, and formation of new synapses. So robotic technologies attempt to leverage the principles of neuroplasticity by improving the quality of movement and increasing the intensity and repetition of the tasks. So that's the whole story about rehabilitation robotics. And they also support and enhance the clinician's task of facilitating recovery and delivering therapy and evaluating patients' progress. There are three types of robotic system. It can be passive, where the patient is inactive and robot moves his hands. It can be active assisted, where the robot partially assists the patient's movement, or it can be active constraint, where the robot forces against patient's movement to strengthen different muscle groups. Rehabilitation robotics can be used in area of neurological as well as orthopedic condition. We'll name them one by one. Stroke, multiple sclerosis, cerebral palsy in children, Parkinson's disease, traumatic and non-traumatic spinal cord injury, traumatic brain injuries, follow-up after brain tumor surgery, degenerative joint diseases of the lower limb like osteoarthritis, follow-up care after inner prosthesis implantation, spinal muscular atrophy, and muscular weakness due to the lack of mobility. There are certain contraindications of the robotic therapy, like when patient is having severe postural instability, he or she is not able to maintain a stable posture, or the patient is having visual problems where patient cannot see the monitor where the robotic therapy is being given. When the sitting or standing position is contraindicated for the patient, like patient is having a deep pressure ulcer or soon after the flap surgery for the pressure ulcer. When the patient needs long-term infusion therapy, we cannot take him to the therapy room. Patients with extremely disproportionate growth of the limbs, like in bone and cartilage dysplasias, where we cannot fit the robotic exoskeleton on the arm, and when there is severe vascular disorders of the lower limb, where an intensive training with the robotic device can induce vascular claudications, In general, patients who have been ordered to remain in bed due to some inflammatory or infective conditions like osteomyelitis of the bone, hip, knee, and ankle arthrodesis, where the joint has been fixed by the surgeon. Patients requiring isolation due to infections like COVID-19 and non-cooperative patients. So when we have a beautiful rehabilitation team in our department, why do you need robotic therapy at all? Let's see what are the advantages of robotic therapy. It is the consistency of the therapy, precision, non-fatigability of the machine, programmability of the device, ability to measure and record in parallel with therapy delivery, and these robotic approaches are capable of functioning at sites remote from the human therapies that can enable tele-rehabilitation, which is of much importance in this COVID era. Now let us see the pictures of some upper limb robotic devices. This is the MIT Manus. This is by Manuon Tract. This is MIME, or the mirror image motion enabler, knee robot, gentle or haptic master. This is the Armin. Now we'll discuss them one by one. MIT Manus was the first rehabilitation robot development of which began in early 90s, and it took over 10 years to become fully operational. It is a 2 degree of freedom system which allows displacement of the elbow and shoulders during hand movement made in horizontal region. During the session, the patient's arm is supported in a non-motorized orthosis, as you can see over here. So let's see something about bi-manual arm. It consists of double handles which permits unilateral or bilateral training of the distal part of the limb. It can be used in passive or active assisted modes. Amplitude, speed, and resistance of both the handles can be set independently, but no feedback is given to the patient. That is the drawback of this device. Mirror image motion enabler. Its distal end is fixed with an orthosis in which the patient's arm is placed. It allows patient to make large amplitude movement in three-dimensional space. So let's see. Knee robot. It can be used in sitting or lying down position. That is the most important factor in knee robot. It can be used in critically ill patients also in lying down position. Here, the therapist moves the patient's arm in the direction in which he is to practice, and the robot records and subsequently repeats the movement. There is a virtual feedback via 3D representation of the patient's arm in the screen can be seen over here in the picture. And the screen informs the patient of the desired movement in the direction to guide his movement. Gentle or haptic master, it is also a 3 degree of freedom robot developed from haptic virtual reality system completed by a heavy suspension system. It can act in passive, active assisted, or in active mode. A large variety of exercises in a 3D virtual environment give the patient and therapist a huge possibility of training parameters, and the performance feedback is given to the patient. Arm guide, this system consists of a handle mounted on a motorized linear slide which can assist patient's movement. It has 4 degrees of freedom. So we can see the development of the robots and degrees of freedom of movement. That means direction in which the patient arm can be moved are increasing day by day. It can also provide active assistance to movement and can also function in active constraint mode, as we have discussed earlier. So it can be used for strengthening also. Hand kinematics and forces generated by the patient can also be recorded. Now coming to the devices which are available in India, they are Armio Spring and Armio Boom. The speaker has worked with this Armio Spring device. So let us discuss about Armio Spring first. How does it act? It provides arm weight support. It gives exoskeleton for movement guidance. It gives augmented performance feedback. It provides grasps and release exercises. It increases active range of motion, it increases strength and endurance of the patient, and facilitates self-initiated movement, also increases the selective control. Here in this short video, you can see the author supervising robotic therapy in a stroke patient. From the face of the patient, you can appreciate that how enjoyable the therapy is for him. It not only engages the patient but also increases the concentration of the patient and also improves the cognitive power, which is very much essential for stroke and traumatic brain injury patients. The problem which we faced in army spring that there was very little scope of improvement of finer hand functions. So the next generation robot, Hexor and Handsome, came, which has the potential to improve the hand functions also. Now, coming to the upper limb robotic prosthesis. Prosthesis is a device that replaces the missing limb and substitute for the limb function. This is Luke arm, which is inspired by the arm Luke Skywalker has in Star Wars. The arm gives feedback to the user by grip pressure control. It allows the user to hold onto a paper cup without even crushing it. And now the bionic hand. It has two unique features. It has separate motors for each and every finger so that each and every finger can move separately. And the thumb also has a separate motor and it can rotate 90 degrees like a human thumb. There are two electrodes which sit on the skin and they record the myoelectric signals which are used by the computer to they translate these signals into into uh, the signals they act by moving the fingers and the thumb. Now coming to lower limb robotic devices. This is Locomat, which can be used in adults as well as in pediatric patients. This is Zero G. This is GEO or the haptic worker, and this is Gate Trainer 1. Locomat, which is commercially available in India, has a motorized body weight supported treadmill with a robotic gait orthosis that assists walking movements of gait impaired patients. It also provides biofeedback on the current gait activity of the patient. Patient obtains natural sensory information through the feet while stepping onto the treadmill, which is an important contributor to motor relearning. Again, the same question comes. When our therapists are given gait training for year after year so successfully, then what is the added benefit of the robot-mediated gait training? This device guides the patient's legs on a treadmill, offering a wide range of training possibilities. It is faster progress through longer and more intensive functional training session compared to manual treadmill training. Physical strain on the therapist is relieved, and single therapist can operate this device. Patients' walking activity is easily supervised and can be assessed. Gait pattern and guidance boards are individually adjustable to the patient's need and patient's needs to optimize the functional training. It can improve patients' motivation to visualize performance feedback. Assessment tools are there which allow easy and reproducible measurements of the patient's progress, and if needed, it can be switched to manual mode. These are some robotic exoskeleton devices which can help to improve the gait and prevent falls that are very common in patients who have impaired mobility. Some of them are commercially available in India, like Rewalk. Rewalk, it is a simple battery-powered system controlled by a wrist-mounted remote that enables the paraplegics to stand upright or even climb stairs. This is hybrid-assisted limb, which is a powered exoskeleton suit currently under development by Japan's Tsukuba University and a robotic company. HAL is being designed to assist the disabled and elderly in their daily tasks, may also be used to support workers with physically demanding jobs such as disaster rescue or construction. The most advanced thing is the mind control robotic arm, where two implants are there in the motor cortex, which take the signals from the motor cortex and reproduce the movement as patient thinks. Like if the patient desires to move a hand, this electrodes will pick up the signals and they will move the robotic device in that direction only. But due to bulkiness of the setup and invasiveness of the procedure of implantation, it is entirely lab-based till now. The long-term goal will be to miniaturize the technology and make the brain-computer link valid so that it can be used by patients at their own home. Numerous Several studies have demonstrated the efficacy and advantages of rehabilitation upper limb and lower limb. Volpe et al. Compared the effect of training patients with robots in acute stroke for 1 hour per day for 5 weeks in addition to the standard therapy to a control group who only used the robot for 1 hour per week. All the 56 patients improved, but the group with more robot rehabilitation showed significantly better improvements in motor power and motor score. A study done on children with hemiplegia from cerebral palsy, trained employing MIT manners, found small but statistically significant reduction in spasticity. This occurred primarily at the elbow after a course of training with Emotion 2 robot. Wills et al. Performed a multi-center trial using Locomat on 20 individuals with incomplete chronic spinal cord injury, 16 of whom were able to ambulate over ground before the study. Overground walking speed and endurance improved for all the ambulators. All individuals who were non-ambulatory at the start were non-ambulatory even at the end. So this is the first published study from India on rehabilitation robotics by the speaker and her mentors, effects of robot-assisted therapy as an adjunct to conventional therapy in upper limb motor recovery after stroke. It was a randomized controlled trial done in the Department of Physical Medicine and Rehabilitation, Vardhaman Mahavir Medical College and Safdarjung Hospital, New Delhi. 64 patients were included and divided in two groups. 32 subjects in control group received conventional rehabilitation therapy using RNU spring, 30-minute sessions per day, 6 days a week over 4 weeks. Assessment was done pre-treatment at 1 month, post-treatment and at 4 months. Outcome measures were Fugler assessment comprises of amount of use score and quality of use score. We have found that improvement observed in the motor recovery of the upper limb in the robot-assisted therapy group was significantly better than that of the control group as measured by FMA for motor recovery of the upper extremity. We have also observed that improvement in the functional of the affected upper limb in the robot-assisted therapy group was statistically of use scores and quality of scores of motor activity, an effective way to improve upper extremity function in stroke patients than conventional therapy alone. To conclude, robotic rehabilitation can make a difference in persons with neurological impairment, but awareness is still lacking among general and disabled people and also among the healthcare professionals. Availability of the robotic systems in India is also a big issue, as till now the facilities are restricted to high-end rehabilitation centers due to its enormous cost of procuring installation and maintenance from foreign companies. The only solution to this problem can be indigenous rehabilitation robots. We are moving forward with our Prime Minister's Make in India drive to improve the rehabilitation robotics scenario in India and bridge the gap between the need of the persons with disability and the availability of the robotic devices. At our institution, we are trying to make and validate an Indian rehabilitation robot in collaboration with our Indian Institute of Technologies. Hopefully, we will succeed in near future. Thank you and namaskar from India.